Last time we introduced the concept of subspaces. Earlier in the fourth lecture we had introduced the abstract concept of linear spaces, and then we started exploring it further, and we found that within vector spaces there are several subsets which do have the same linear space structure, and they were called the subspaces. I mean, they are very important. So, I am not going to go back into that. Now, we explore the linear spaces and their geometry further, so that we get a much finer understanding of what linear spaces are. First of all, so as it is the best way is to look at some examples and then come to the ideas. So, our most favorite examples are R, R2, R3 over R. We have already seen that they are all vector spaces. They are standard examples of that, and we also have a geometric picture of that. So, we exploit that and to have an understanding of the ideas. We found that suppose you go to R2, then you see that what are the subspaces of that? The vectors, the subset consisting of 0 vector is a subspace. The subcollection of elements in R2 which form a line through the origin, any line through the origin is a subspace, and the whole space is a vector space. Now, you can actually prove that or compute that any subset which is a subspace is in one of these forms. Either it is the 0 vector, or it is some straight line passing through the origin, or the whole space in R2. In R3, the analogous picture is you have the 0 vector again, then all lines passing through the origin, all planes passing through the origin, and the whole space. That is what you have. Okay? But we want to have a more deeper understanding of this, and in the general scenario we have to look at what exactly this means or how we can rework on them. We said that Rn is a vector space. So, in Rn we cannot picture it, still we want to have an understanding of what the subspaces. Now, coming back to the R2, you recall that in my earlier lectures that suppose you choose a non-zero vector, because you see that in R2 every point can be identified with a vector. So, there is a 0 vector and all others are non-zero vectors. Suppose I call this U. Now, scalar multiples of U will generate a whole line passing through the origin, but that does not account for all the vectors in R2. Now, if you choose some other vector again on the same line, and what is the operation that we have in our hand? It is addition and scalar multiplication. With that you cannot generate the whole of R2. Therefore, we observe that suppose I were to choose another non-zero vector which is not lying on this line, okay, and then the scalar multiplication of this will give you this entire line, and all other vectors can be reached as a sum of a vector in this, suppose I call this u and this is w, let me call this w. So, if u is a subspace generated by u, w is a subspace generated by w, then you can express any vector in R2 as a sum of a vector in u and a vector in w uniquely. How does that happen? Just recall, suppose you take this vector. Now what you do is, you keep this as the diagonal of a parallelogram with the sides on these lines. So what you do? You complete the parallelogram. Complete the parallelogram and that will fix a vector here, a vector here. Okay? And you see that this particular vector that you have chosen is essentially the sum of these two vectors. But what is this? This is essentially a scalar multiple of u. This is a scalar multiple of w. So, if your vector is denoted by v, v is sum alpha u plus beta w belonging to R. We are working in R2, so the field that we take up is R. Therefore, we find that you do not have to know every vector of R2, but all that you need know is a carefully chosen pair of vectors. With that, with addition and scalar multiplication, you can generate every vector. Okay, right? So that leads to, or that idea generalized will lead to the concept of what is called a basis or a coordinate system that you can use. In fact, the Cartesian coordinate system that we originally use is 1 0 0 1, they are vectors. So, this is a vector, this is a vector, and you have the vector space generated by this vector, that is the your x axis, and the vector space generated by 0 1 is the your y axis. Now, any x y can be written as therefore, these two, using these two vectors you can get every vector in R2 generated. Now, this is an idea that we have in our mind and we want to take this up in the abstract scenario. Similarly, in R3 also, I do not want to go to the details, but you know it already. Because you can choose, if you choose a non-zero vector, it will generate a line. If you choose another vector which is not on that line, it will generate another line. Together it will generate a plane passing through the origin, which does not cover the whole space. Now you can choose a third vector which is not lying in this plane. Such a vector exists because this does not cover the whole R3, and taken these three vectors together, they generate the whole space. So, that will give you a coordinate system. So, in fact, there are several coordinate systems that you can use for R2 depending on the circumstances or which is advantageous to you in a problem. Then you can choose the appropriate coordinate system. Always the rigid orthogonal system that you use may not be the ideal one for in a problem. That is just a caution. So, what we are trying to develop is a coordinate system for a given vector space. Now, for that we have to look at the following. Now, you see that if you take these two vectors and take the span of it. What do I mean by the span of it? I think in my last lecture I said what is the span of it. It is the set of all linear combination of these two vectors with all scalars picked up from R. So, that span becomes the whole space, or in other words these two vectors span the whole space. At the same time, we also observe that just one of them will have its span only a line, it is not the whole space. Okay. So, you have to add another vector. Okay. So, if you choose a second vector which is again in this subspace, it is not going to span the whole space. In the case of plane, it will be, in the case of R3 it is more clear. Now, as far as the complexities are concerned, it will be more clear because you take two vectors which are not along the same direction, non-zero vectors, then you see that they span a plane. If you take any vector lying in this plane along with the other two and go for the span of it, you keep generating only this particular plane, okay, right. But you have to be careful about the choice of the third vector, so that you reach out to all the entire R3. So, let us now come to the general scenario and start looking at these properties. Please keep these things in your mind. So, we start with a vector space V over a field F, the usual addition and scalar multiplication. Now, we define a few things like what is called the span of a set of vectors. So, you have, suppose the collection is a collection of k vectors. Okay. Now, the set of all V, where V is equal to alpha 1 V1 Vk with alpha I belonging to F. This collection you call this some S. So, S is now the span of the vectors V1, V2 etc. Vk. I am not putting any restriction on V1, V2, Vk. Okay. They are just k vectors, that is all. So, S is certainly a subspace of subspace means it is a vector space in its own right. Now, what we are looking for is a set of vectors which will span the whole space. Okay. So, this is our objective. And second part of this objective is this: we do not want far too many vectors to do this. For instance, you take R3. In R3, suppose I take these vectors 1 0 0, 1 1 0, 1 1 1, 1 2 1, and take some 4 or 5 vectors of this kind. Now, suppose you take these 4 vectors, then the span of that is the whole of R3. Sometimes even if you choose 4 vectors, it may not span the whole thing, because after all you choose 1 0 0, 1 1 0, then you take 2 1 0. These are 4 vectors, but you can easily see that it does not span the whole space. okay, needs little bit of computation, okay, so that these 4 vectors do not span the whole space, which by just producing a vector in R3 which is not a linear combination of these 4 vectors. So, you cannot say whether just taking k number of vectors, you cannot say that it is going to span the whole space. So, it is in general a subspace, but what we are looking for is a certain number of vectors which will span the whole space. At the same time, that is also optimal in the sense, if you drop one from them, it will not span the whole space. So, such a set of vectors is what we are looking at, okay. It has certain advantage. So, this does not so we define certain things. We already introduced linear combination last time, okay. Now, we, as I cautioned in my last lectures, that when you write a linear combination, only a finite sum makes sense, because we have only an algebraic structure where you can add, you can scalar multiply, but you cannot write down an infinite sum. If you want to make give a meaning to an infinite sum, you need more tools or more structure like convergence or a norm and so on, okay. So, that is not there, we are only having the algebraic structure for the space. Therefore, within that what you can write is, you can add 2 vectors, you can add any finite number of vectors because you can repeatedly add, but only finite sum makes sense. And I also gave an example where I formally wrote an infinite sum, but then caution that it has to be, it has to have all but finitely many terms 0. This was the situation, talked about polynomials over R. Then I had this set of vectors, it is an infinite collection that you have. Now, one can write a polynomial in the form, this is a formal sum. With the t to the power 0 taken as 1, okay. But this sum as such does not make any sense, because we do not have the supporting structure that you have, but this means with all but now what happens, essentially it is a finite sum which is a polynomial, you know, and you can talk about the degree of the polynomial, etc., etc. So, every polynomial can be written in this form by adding terms with the coefficients set as 0. This has some advantage when you take the sum of 2 polynomials and you write that, or when you especially only in that case it has some advantage. Otherwise, you have polynomial of degree m, a polynomial of degree n, then you have to write, and then you know you have to make assumptions like m greater than n, n greater than m, and these kind of assumptions will be required. So, here no such assumptions are required, you can straight away write down the sum of the polynomial. So, whenever we talk about linear combination, it means essentially it is a finite sum. Okay. Although we call this a linear combination, okay, but because we have put this extra restriction, it has a meaning. Now, what I want to introduce is the spanning set. Okay. So, if S is S this notation we have introduced, this notation is essentially this one, sorry. Is equal to, okay. That means you take all possible linear combinations that accounts for all the vectors in V. So, we are now looking at spanning vectors, a collection of spanning vectors, and then we have to, as I said, we have to go for the optimal class. So, what do we need further? We have to introduce the concept of that optimality by introducing what are called linearly independent set of vectors. So, linear independence. I will define linear dependence. A set of vectors linearly dependent if there exists scalars C1 Ck, not all Ci equal to 0, such that C1 V1 this is what you call a linear combination. So, you want a linear combination to vanish, and that should not be a trivial linear combination, because a trivial linear combination always vanishes. Trivial linear combination is the one where all the Ci's are 0. Okay. So, we want a non-trivial linear combination to vanish, then you say the vectors V1, V2, etc., Vk are linearly dependent. And this is something that we have insisted on, not all Ci 0, some of the Ci's may be 0, but at least one of the Ci is different from 0, okay, which in turn tells you that if your collection has 0 vector in it, then that collection is always a linearly dependent set. Another inference that you can immediately make is that every superset of linearly dependent set is linearly dependent. So, every superset means a set in which the given set is a subset. Okay. So, if you take this V1, V2, Vk and adjoin to it some more vectors, then it is always linearly dependent. Now, we say that using this we can define linear independence, a subset which is not not linearly dependent is called a linearly independent set. Now, immediately one can prove an equivalent statement. An equivalent statement of linear independence is this. In fact, I think you should attempt the proof of that. Linearly independent if and only if C1 V1 plus I think you should try to prove this. Okay, starting from here, proving this. I mean, these are small little things which can strengthen your mathematical skills of proving results. Okay, so I don't want to spend time on that. Leave it to you as an exercise. So. Okay. Now what we do is this, the following. We go back to this example. Now you see that these 4 vectors are linearly dependent. That is quite easy to prove, because you see that this one, it's quite easy to see that 1, 2, 1 can be written as a linear sum of the other 3. You can work it out actually, or any one of them can be written as a linear sum of the other 3. That can be easily worked out. It's a matter of solving some linear equations. Therefore, you see that all the 4 is not essential to describe your vector space. You can knock out one of them, because since if this is written as a linear combination of these 3, then if you have a vector expressed as a combination of these 2, the part of this can be replaced by that particular combination that you have. Therefore, only 3 of them is required. Okay. So, you see that essentially you have a subcollection which is linearly independent from this, and that also spans the whole space, and such a collection is what you call a basis or a coordinate system. Okay. So, we define a basis . A linearly independent collection of vectors spanning basis or a coordinate system. Now, one more caution. See, this collection is a linearly independent subcollection, but here it is an infinite set of vectors. So, what do you mean by that? Okay. Every finite subcollection of that is linearly independent. So, that has to be clearly understood, okay, because we said only finite sums do make any sense. Okay. So, every finite subcollection of 1 t, t square etc. is linearly independent. Therefore, we say this is linearly independent. So, when you talk about the linear independence of an infinite collection, it means in the context of a linear space that every finite subcollection is linearly independent. That is important to understand. Second thing is that every element in PR can be expressed as a linear combination of this. Therefore, this forms a basis, although it is not a finite collection. It forms a basis for PR. Okay? But suppose you go to a larger class of vectors like all continuous functions defined on the interval 0, 1. You know that all polynomials are also continuous functions over the interval 0, 1. Okay? And it is a proper subspace of continuous functions over the interval 0, 1. Now, the PR can be spanned by this, but you see that if you take continuous functions over the interval 0, 1, this does not span it, because any finite linear combination of vectors from 1 t, t square etc. is going to be only a polynomial, and there exist continuous functions on the interval 0, 1 which are not polynomials. So, you cannot reach out to elements which are not polynomials. Okay? So, these are some of the remarks that are useful. So, henceforth I think we will stick to the so called finite dimensional vector spaces. So, let me just make what I mean by a finite dimensional vector spaces. Finite dimension. Consisting of finitely many vectors. Right now, I have not defined dimension so far. Okay? So, right now, the word dimensional is to be understood just a term, just saying it is finite dimensional. Later, you will link it up with the word dimension when we explore it further. Okay? Right now, we say that if you have a basis consisting of finitely many vectors, then you say that space is finite dimension. It is just a name at this stage. Okay? Now, we will go to define what is a dimension, which needs some more steps. Okay? So we will explore this. So, remark is now at this stage a word introduced, nothing more than that. So this is just a name. So let us explore this further. So we want to show that given a spanning set, you can construct an optimal class from it, some method, so that you get a basis. Okay? So that is the first thing that we do. So we assume, we start with, so we assume V is dimensional. That is assumption, which means it has a basis consisting of finitely many vectors. So let us start with any spanning set of this and also some linearly independent subsets of that, right? Not necessarily both properties are there for these sets. So we will make some comparison of the relative what is called a measure of these two, in the sense how many elements are there in these collections and so on. Okay? So a basis for V. Okay? There may be another basis consisting of possibly m vectors, we do not know. All that we have said is there is a finite set of vectors which spans it. So one thing is clear, that a same vector space may have several bases, that is clear. Okay? So even our examples do provide you with the case of that. The same vector space may have different bases or different coordinate system. Okay? Still, one of the feelings that you have looking at the geometry of R2 is that suppose you choose two different bases, you feel that, or you observe that they have the same number of vectors. How many in that case? Just 2. Okay? In the case of R2. In the case of R3, you see that any 2 different bases that you choose has the same number of elements. So our question is this: suppose you choose 2 different bases for the vector space. Okay? How many, do they have the same number of vectors? Our experience tells you yes, but in the general scenario you need a proof for that. Okay? You cannot accept it just like that. Some examples of something happening that cannot be straight away generalized into a theorem, but you can make a conjecture, and possibly if you can prove it, then it becomes a theorem. Okay? So the question that you ask is this: from R2 and R2, we have seen that choice of different bases are possible. And they have the same number of elements. In R2, every basis 2 elements, and in R3 these are the observations that we make. Okay. So, can you work on this in the general scenario or along the same lines in the general scenario? One of the things that you observe is this. See, if you have a linearly independent set, I said it can generate a subspace of it, not necessarily the whole space. Okay. Therefore, what you can possibly do is put in more vectors into that collection and make it a basis. That means a basis for the given space. Okay. So, how do you do that? We have done it already. What did we do? In R2 we have chosen a non-zero vector u. The subspace generated by that is a line which does not cover the whole space. Now you choose a second vector which is not on this subspace, okay, and then consider this u and w together. You can see that every vector can be written as a linear combination of u and w. Okay. So, if a collection of vectors, say linearly independent vectors, do not cover the whole space, what you do is bring in additional vectors which can be chosen, and so that you can continue this process until you get a cover the whole space. I mean, this is roughly the idea that we use. Okay. So, one of the results that we obtain at this stage is this. Let then what you can say, there exists a basis consisting of finitely many vectors. That is just the definition. So, there is a basis consisting of n vectors. Now, what we want to show is that suppose you have a set of linearly independent vectors, okay, then if it does not form a basis already, then you can adjoin more vectors and enhance this to a basis for the space. So, then we may construct a basis for V with U1 as a subset. That means bring in some more vectors and make it a basis. Okay. Now, to prove this result, we need another result. Another result is this. Suppose, so let not necessarily the same k, so I can use another dependent vectors what you can show is that suppose you list it out in this order u1, u2, etc., uk, what or um. So, what you can show is this. You can find some uk such that uk can be written as a linear combination of u1, u2, etc., uk minus 1. Okay? Right? How do we do that? We go about doing it. I mean, see the okay, I didn't state the theorem. Then there exists k to such that uk can be written as a linear combination of C1, U1, U2, etc., uk minus 1, the previous ones. Okay. So, you know that this set U1, U2, etc., Um is linearly dependent. What you do is you start with U1. Of course, U1 is a singleton non-zero vector, so it is linearly independent. Now, you take U1, U2. Okay. If U2 is already a scalar multiple of U1, you have got the corresponding k. If not, if U1 and U2 are linearly independent, then you look at U3, whether U3 is a linear combination of U1, U2, okay, and so on. You will reach somewhere, you are going to find a k, uk such that uk can be expressed as a linear combination of u1, u2, etc., uk minus 1. Okay. Now, in the worst scenario, um is going to have that property. No? Suppose um does not have that property, what does it mean? It means that u1, u2, etc., um is linearly independent set, but our assumption says that it is a linearly dependent set, and that is how you prove it. If you are interested, you can look into the proof of this it with almost finite dimensional vector spaces. Okay. So, this result is very useful in proving the sum of these results. So, what one does is, the strategy is here, that is, we may construct a basis for V with U1, U2, etc., UK as a subset of it. We have assumed that this is a linearly independent set. So, how do we proceed? See, V is finite dimensional. Then there exists V1, Vn, finitely many elements, A, a basis for V. Okay. But what we are looking for is some basis of which this U1, U2, etc., UK is a part. So, we have to somehow bring that in. Okay. So, what do? You start, you see that this is a linearly independent set, and also it spans the whole space. That is the property of V1, V2, etc., Vn. Therefore, you take this one, say, look at this collection, that is, you take UK consider, what can you say about this? This is already linearly dependent. What does it mean? Apply this result. Okay. You can find some Vi somewhere here, so that Vi is a linear combination of the preceding elements, that is UK, V1, V2, etc., Vi minus 1. Drop that. Okay. Throw that out, because you do not need it anymore, right? And you know that this collection spans the whole space now, because whatever job I think this UI was serving can be served by this set of elements once UK is therein. What is the next step? You put UK minus 1, UK, V1, Vi minus 1, Vi plus 1, Vn. Take this. Okay. Once again, by the same sort of argument, you can see that this is a linearly dependent set. Okay. And you can find some Vj which can be expressed as a linear combination of the predecessors. Okay. Drop that also, and continue this process until you exhaust the whole process. Now, you will see that you are not going to exhaust these set of elements before you exhaust them. Okay. Right? Because you can prove that. Again, I leave the proof to you. See that the process, what you call, does not exhaust V1, V2, etc., Vn before you bring in all these U1, U2, etc., UK. So, once you do that, then you see that the new collection is going to be a linearly independent set which also spans the whole space, and this becomes a basis. Okay. So, you understood the procedure, how you do it. So, that is just the outline of the proof. Essentially, what we would like to prove is that any two different bases of a finite dimensional vector space will have the same number of elements. Okay. So, this is the major result. Basis elements. This is the main result that we prove. How do we prove this? So, we will take two bases, B1 consisting of so let what we claim is that M is equal to N. So, you see, you look at B1 and B2, both have the properties, namely they are linearly independent, they also span the whole space. Okay. Right. So, now what we do is, for the time being, we look at B1 as a spanning set, okay, and B2 as a linearly independent set. B2 as a linearly independent set. Now, what one does is the following. You know that from our experience of the examples, we know that the spanning set may contain more elements than required, and the linearly independent sets may fall short of the required number of vectors. So, in general, what we are going to have, see, B1 is a spanning set consisting of m vectors. So, we expect m to be bigger than n, because this is, we are only looking at as a linearly independent set. So, the proof that we are going to give is that we prove m is greater than or equal to n. If you prove that, then you have done. Why? You can switch the two sets B1 and B2, okay, and get the same inequality, I mean the different inequality, namely n is greater than or equal to m, so that m is equal to n. Okay. So, it is enough to prove just for if B1 is a spanning set and B2 is a linearly independent set, then the number of elements in B1 is greater than or equal to the number of elements in B2. Okay. So, how do we work on this? So, we once again apply this type of technique. Okay. Take the spanning set is This is the spanning set. Okay. Now what you do is you start bringing in one element at a time on this. So you consider V n, okay, then certainly this spans the whole space, right, because u1, u2, um spans the whole space. We have introduced one more vector and this spans the whole space. Now what you can do? You can apply that result. It says there is some ui here. Ui can be expressed as a linear combination of the predecessors. Okay? If you pick on that ui, drop it. Okay? Then what is the next stage? So you from here you find there exists ui is linear combination of I minus 1, this collection, right. Now drop ui. What do you do? So you have now this collection Vn um. Once again this spans the whole space, no problem. Okay. What you do as the next step? The next step is we have already brought in Vn. Now we put Vn minus 1 Vn this is a linearly independent set, dependent set. So what happens? You can find out some uj such that uj is a linear combination of the previous ones. Drop that and then you keep on doing it, and you can show that since this is linearly independent, you need a small little argument. See that you exhaust u1, u2, what is that, v1, v2, etc., vn before you exhaust this class. Okay, right? Or at best you may, if they are equal, you may exhaust it at the same time. Okay, so you get an opportunity. You don't exhaust this first, so that you have some more vi's left here. What would then that mean? That would mean suppose you were to exhaust this first, then what happens? You would have come to some u j onwards, uj plus 1 etc., um will be a spanning set for the whole space. Okay? But you know that it is a linearly independent, because any subset of a linearly independent set is linearly independent. Therefore, this will be a basis, okay, which cannot happen, because you already know that u1, u2 etc., un, or sorry, what is that, v1, v2 etc., vn is a basis or a linearly independent set, which is not possible. Okay. So, what does it indicate? It indicates that the m is certainly greater than or equal to n. That is one part. Now the converse is quite easy. because you switch the role of B1 and B2. You consider B2 as a spanning set and B1 as a linearly independent set and make the same argument, get the result. Therefore, you get M is equal to N, which shows that any two different bases that you choose for a linear space is having the same number of elements. So, irrespective of what basis you choose, there is a number that is getting conserved, namely the number of elements. You cannot work with less number of elements. That is the thing. You need not require anything more than that. Although the choice of the basis is not unique, but the number of elements in a basis is a unique number, and that is a sort of intrinsic number associated with the vector space, which you call the dimension. That is why I said I didn't define what dimension is earlier. I simply used finite dimensional. Okay. Here, this is the first place where I am talking about dimension. I am able to talk about dimension because it is an intrinsic number associated with the space, irrespective of what coordinate system you use. Okay. You can see this fact coming over and over again, that there are several bases that you can choose for the same vector space. Okay. That really makes things, life, more exciting as well as hard in working in linear spaces. So, I think I will stop here. Okay. This is the right place to stop with the first lecture. Thank you very much. If you have any questions, we can discuss questions later, no?